publication, including a few book chapters and conference paper. Currently, she is working on 2 review and technical paper. Now, I would like to directly go to our today's speaker. Welcome, Rizwana Abdin ma'am. I would like to request you to talk about our session. Thank you.
Thank you so much. Can I share my screen?
Yes, you can.
Thank you, sir. So I hope you can see the screen. Okay. Honorable Chair and Coordinator of our DEEE department, other faculty, staff, and my beloved student, very good evening, and thank you so much for giving me the floor to present my research work that I have conducted in my master's thesis period. So the topic of today's seminar is design and fabrication of MWCNT PDMS composite polymer-based flow sensor for low fluid flow detection. So basically today I'm going to describe my research work that I have conducted in the thesis period of my master's degree. So before I jump to my work, I would like to describe something that is related to nanotechnology. So what is nanotechnology? We know that 1 nanometer is equals to 10 to the power minus 9 meter, which is 1 billionth of a meter. But how we can define the size of 1 nanometer? For example, if I show you this calculator, we can say that the length of this calculator is 10 to 12 centimeter. If I show you this much, you can understand that this is 1 centimeter. Again, if I want to define the size of 1 millimeter, I can say that the thickness of any A4 paper that can be around 1 to 0.5 millimeter. How we can define 1 nanometer? Is 1 nanometer visible to us? Can we see 1 nanometer particle with our bare eye? No, we cannot see 1 nanometer particle from our bare eyes. For example, if you see this image, here you can see one zoom-in image of human hair, a single human hair, which is about 1 lakh nanometer. And beside that human hair, you can see some nanofibers, which is around 1 to 5 nanometer. So I hope you can understand how small a nanometer or one nanoparticle is. Now, what is nanoscale? Or which particles we can say that they are nanoparticle? The particle which has dimension equal to or less than 100 nanometer particles are called nanoparticles. And the science where we can study the nanoscale materials and their different properties and phenomena, that science is called nanoscience. And finally, the nanotechnology is nothing but the application of nanoscience to control the matter at their atomic level to improvise different electronic devices or any composite material is called nanotechnology. I would like to show you some other examples to understand how small the nanoparticle is. For example, if you divide the diameter of Earth with 51 million, you will get the diameter of 1 basketball. And again, if you divide the diameter of the basketball with another 51 million, we will get the diameter of a nanoparticle. So I hope you can understand or you can imagine how small a nanoparticle is. And when the diameter or the particle size will decrease that much, it will start behaving in different way. Why nanomaterial behave in different way? There are a few phenomena for which reason nanoparticle behave in different way. The first one is the gravitational force in nanoparticle is very negligible. Rather, the electromagnetic force become dominating. Again, in case of nanoparticle, the quantum mechanics is more effective than of the classical mechanics model. The third one is very important one, the surface area. When we will reduce the size of the particle and reach to the nanoparticle size, the surface area will become extremely high. That is why the surface area to volume ratio will be increased. And finally, the random molecular motion become completely different in terms of the nanoparticle than the bulk material. Because when the size of the nanoparticle is very small, it becomes extremely light. So the movement of the nanoparticle is quite different than of the same material of bulk material. Now, if I emphasize on the surface to volume ratio of nanoparticle, here in this image, we can see in the first one is a cube with 1 centimeter dimension in each side. And the surface area of this bulk material is 6 centimeters square. And this cube has 6 surfaces. Now, if I divide this bulk material into several smaller cubes, generally what will happen, the surface area or the surface number of surface in that bulk material will be increased. So naturally the surface area is also will be increased. If I break that bulk cube further smaller section, what will happen, the surface area will be increased dramatically. So from this discussion, I hope you can understand that when we deal with the nanoparticle has way more larger surface area than the bulk material. That is why nanoparticle become much more interactive, or they can participate in higher rate in the chemical reaction than of the same bulk material. Here you can see one structure of 60, which is named as buckyball, and this is the very first man-made nanostructure, which was invented by these 3 gentlemen who got Nobel Prize for this structure of nanoparticle in the year of 1996. Now, this is one type of carbon nanoparticle where different carbon atoms are connected with covalent bond in different shape. There are 2 different ways basically to synthesize or to make any nanomaterial. First one is top-down approach, where from a bulk material it is grinded into a powder, and then from the powder the nanoparticle can be formed. And here the approach, for example, mechanical grinding, etching, lithography, ball milling, etc. All these methods are used to follow the top-down approach to make nanoparticle. And the second one is the bottom-up approach, where the nanoparticles are made from the atomic level. The manipulation is done from the atomic level to make the nanoparticle. And some of the bottom-up approach are chemical precipitation, gas phase, agglomeration, self-assembly, sol gel technique, and so on. In my research, I basically followed the bottom-up approach, which I will discuss in the next slides, other next slides. So if I go for the application of nanotechnology, nanotechnology has application in a very widespread area. It can be useful in energy section. It can be useful to develop the textile materials. It can be useful to waste management or develop any composite metal. It can be useful in to fabricate electronic processor or different sensors and so on. Here in my research, I have utilized nanotechnology to develop a low flow sensor with which I can measure different flow rate of fluid at a very small rate, for example, microliter per second. So now I will start my research part. So I have mentioned that I have worked with a flow sensor. Now, what is a flow sensor is? A flow sensor is nothing but a device which is used to measure the flow rate of fluid passing through the device. And this measurement can be done by means of different mechanical or optical or electrical phenomena. And what is the importance of the flow sensor? Flow sensor can be useful to measure the flow rate of fluid at household. Also, it can be useful to measure the flow rate at industrial purpose. The flow sensors can be useful to measure the flow rate at different civil structure. And lastly, the flow sensors can be useful to measure different flow rate in medical devices. Now, coming to the importance of low flow sensors. Low flow sensors can be applicable to measure the blood flow rate. It can be useful to analyze the cytometric analysis. It can be useful to measure the flow rate of fluid in capillary pipe. Low flow sensors can be useful to measure the flow rate of fluid in our surrounding environments. They can also be used to measure the airflow rate in different electronic devices. In the literature, we have been seeing that low flow sensors have been used for cytometric flow analysis. They can also be used for controlling the drug delivery system. Also, the low flow sensors can be used to measure the airspeed of different mini aircraft or mini drone. Now, in this slide, here, different techniques to measure the low flow rate in different devices are illustrated. If I start with the very first diagram, which is the vortex flow meter. In vortex, basically, the flow rate of the fluid can be measured by creating the vortex inside the flow channel. In case of optical flow meter, the flow rate can be measured using different optical phenomena of the fluid that is passing through the channel. In electromagnetic flow meter, the electromagnetic phenomena of the fluid can be utilized to measure the flow rate of the fluid. Now, coming to the Coriolis flow meter, the flow rate of the fluid can be measured from the angular deflection of two parallel connected flow channels. In case of thermal flow meter, the flow rate can be measured from the change in resistance due to the thermal effect balanced Bridgestone bridge. And finally, if I talk about the cantilever-based flow sensor, the flow rate can be measured in cantilever flow sensor from the deflection of the cantilever sensor. So there are, we can see that there are many techniques to measure the low flow sensor. There are other sensors which I didn't include here. So more or less, the main problem in all of these sensors deals with the complexity in their design and execution method. Also, a very few low flow sensors are portable. And finally, almost all of them are quite expensive in terms of their usage and execution method. So, from all these problems, I tried to fabricate and develop a flow sensor, and for that purpose, the following objectives were used. The first objective to fabricate the sensor was to fabricate an electrically conductive MWCNT PDMS film. The second objective of this thesis was to evaluate the fabricated MWPDMS film in terms of electrical and electromechanical characterization. And finally, after the characterization, the film was implemented inside a flow channel to check different flow rates of the fluid at. So first step, the synthesis of the MWCNT PDMS thin film, where carbon nanotube PDMS mixture was prepared and it was cured with different electrode gap configuration. After the fabrication, the film was characterized electrically, where IV characteristics curve was generated for different concentration and different electrode gaps. Then the surface characterization of the film was performed using the water contact angle. And in the third step of the characterization, the mechanical characterization was performed, where the tensile test was done to check the flexibility or elasticity of the film. And finally, in the characterization, the electromechanical characterization was performed, where the change for different bending angle was observed. Then in the third section of the methodology, basically the fabrication of flow channel and was performed using 3D printer technology. And finally, in the fourth step, the system was assembled with the fabricated thin film, and the flow type and the position of the sensor inside the flow channel was analyzed. And after that, different flow rates were checked whether the sensor can detect the different flow rates or not. So now I am going to describe the methodology one by one. First, the synthesis of the carbon nanotube PDMS composite polymer. So in this section, what I was done, the carbon nanotube PDMS was mixed together. PDMS is nothing but resin-like polymer. So specific amount of carbon nanotube was mixed with a specific amount of PDMS under a magnetic stirring for about 10 minutes. After that, the curing agent was added to this mixture and it was magnetically stirred for another 15 minutes to get a homogeneous mixture. After we got the homogeneous mixture, it was sprayed on a mold, a 3D printed mold with a thickness of 0.5 millimeter. It was cured under 80 degrees Celsius for 2 hours. And after 2 hours, we got our desired MWCNT PDMS thin film, which was later implemented in the flow channel. So after the fabrication of the film was characterized electrically. So when the film was characterized electrically, the electrode was used, the aluminum was used as the electrode, and different concentration of carbon nanotube inside PDMS, for example, the concentration from 1 to 20 weight percentage was fabricated, and it was found that up to below 8 weight percentage, the film was not showing any conductivity. But when we increased the concentration of carbon nanotube from 8 to 12 weight percentage or more than that, it was showing a good conductivity inside the film. And also different electrode gaps from 0.5 millimeter to 10 millimeter was observed to characterize the film. I will show you the data in the result and discussion part. So here you can see that different dimensions of the film was fabricated for different purposes. For example, in case of the tensile test, electrical characterization, and for the implementation in the system, the same thickness of the film was used, which is 0.5 millimeter. But there was a little bit change in terms of the length and width for different purposes. After the electrical characterization, the surface characterization of the film was performed. Before I go for the method, I would like to describe two things. Basically, there are generally two types of surface. One is hydrophilic surface, another one is hydrophobic surface. In hydrophilic surface, what happens? The surface loves the water. That is why it attracts the water, and the water gets sprayed on the surface. Therefore, the water contact angle between the surface and the water become less than 90 degrees. Opposite thing happens to hydrophobic surface. The hydrophobic surface doesn't like the water, so it will not attract the water, and the water will stay as a drop on the surface. Therefore, the water contact angle between the surface and the water will be equal to or greater than 90 degrees. Now, here, when I observed the water contact angle of my film, I found that when I was increasing the concentration of carbon nanotube inside PDMS, the water contact angle was increasing, and in every cases, in every concentration, I found that the water contact angle is greater than. That means my film is hydrophobic. When I will flow the fluid through the channel, it will not get stick to the film, which is desired. Now, in mechanical characterization, the tensile test was performed to check the elasticity or the flexibility of the film. Because this test was performed because since we are depending on the change in resistance due to the bending in the film should be very much flexible. Otherwise, it will not get bent, and there will be no change in the resistance. So, 3 identical samples for each concentration was chosen to perform this test, and the stress versus strain curve was generated to check the elasticity. And finally, using the Young's modulus, the elasticity of the film was concluded. Now, when I performed the electromechanical characterization, basically in the film, there were 2 electrodes, and the 2 electrodes was connected with 1 ohm meter, and one side of the film was stepped strongly, and another side of the film was pulled upward to make bending from 0 to 3 degree with 0.5 degree interval. And this formula was used to calculate the the bending, because this is a very small bending. It cannot be checked from bare eye. That is why I have chosen this formula, from where the x is the thickness of the the length of the film, and the vertical reflection was measured using a digital indicator. And from here I got the resistance versus bending angle curve. After that, the flow channel was fabricated using the 3D printer, which is a very useful device. We can fabricate any device that we design using this 3D printer. So as you can see that my flow sensor has basically 2 part. One is the upper part and another one is the lower part. In the upper section, we have the flow channel, and we have one lower part where basically the film or the sensor that we have fabricated will be inserted here. And after we place the sensor here in this 2 chamber, the upper part will be covered on top of the lower part. And the diameter was taken basically 5 millimeter for the flow channel. Now, as I have mentioned that the sensor or the film that we have fabricated was inserted inside the 2 chamber of the lower part. This is the testing sensor. You can see, and this is the reference sensor. if you notice carefully, you can see that the reference sensor is not exposed. It is hidden inside the chamber. So when the fluid will flow, it will not affect the reference sensor. So there will be no change in the resistance here. But here you can see the testing sensor is exposed to the open channel. Because when the fluid will flow through the channel, due to the flow rate, there will be a force on this film, and it will get bent. And due to the bending, the electrode gap between the electrodes will be changed, and depending on that, there will be a change in resistance. And we can characterize our, the system using these characteristics. So this is the final sensor. You can see the upper chamber and lower chamber. This will be assembled like this. And when I tested, I basically followed this layout. The liquid was passed through one infusion pump, from where we can provide different flow rate to check the performance of the sensor. And the output of the infusion pump was inserted inside the the flow channel of my sensor. And here, as I have mentioned, there will be a testing sensor which will be exposed to the flow channel, and the reference sensor will be hidden inside the chamber. So when the fluid will flow through this channel, it will bend the testing sensor, and due to the bend, there will be a change in the resistance, but there will be no change in the reference sensor, since there will be no effect of the flow on this sensor. So there will be no change in the resistance. Now, if I go to the result and discussion section, on the very first, I would like to discuss about the configuration of the nanotube that we have used as the sample. This is basically the SEM, or scanning electron microscopy, zoom-in image of the carbon nanotube. So after having this image, I took the diameter of the carbon nanotube for 50 times, and I calculated the average diameter of the carbon nanotube, and it was around 39.8 nanometer. And from the Raman spectroscopy, it was found that in the sample, we found one D band and G band, which is indicating that the carbon nanotube is formed. Now, coming to the mixture of the carbon nanotube with the PDMS, I found some different behavior when I was changing the concentration of the carbon nanotube inside the PDMS. What I found that when the concentration was low, for example, 0 to 8 weight percentage, it was quite easy to the carbon nanotube with the PDMS using the magnetic stirring. But when I increased the concentration at 10 to 12 weight percentage, it was a little bit harder to mix them homogeneously, because the carbon nanotube was dominating the PDMS matrix. And in case of 15 to 20 weight percentage, it was not possible to mix them homogeneously, and therefore I could not fabricate a thin film with 15 to 20 weight percentage. That is why I selected 10 and 12 weight percentage thin film for my final sensor. Now, in case of electrical characterization, the IV characteristics curve for different concentration of MWCNT PDMS generated, and it was found that in case of 5 weight percentage of MWCNT, no conductivity was found and the resistance was 0. But when the concentration of the carbon nanotube was increased in PDMS, for example, at 8 weight percentage, a little conductivity was found inside the film, and the resistance in that case was around 18.16 kilo ohm. Now, for the further increment in the concentration, for example, 10 and 12 weight percentage, the conductivity increased dramatically and the resistance was decreased to 4.17 kilo ohm and 2.55 kilo ohm respectively. So we can see that with the increased amount of concentration, the conductivity is increasing with the other characterization. Another IV characteristics curves was generated for different electrode gaps in the film with 10 weight percentage and 12 weight percentage. And it was found that for same electrode gaps, the amount of current was much higher in case of 12 weight percentage than of 10 weight percentage. So I decided to use 12 weight percentage since it is showing a significant amount of current or resistance. After that, from the result of tensile test, I found that with the increased concentration of carbon nanotube inside PDMS, the film became more elastic since the elastic modulus was increasing. So this change was gradually to 10 weight percentage, but when I increased the concentration up to 12 weight percentage and 15 weight percentage, this elasticity increased in a dramatic manner. So, and another thing was found that the stress versus strain curve that was generated from the tensile test, all of them was giving its response at its linear region. And this is indicating that my sample is elastic. Now, from the elastic modulus formula, we can see that the elastic modulus basically depends on the force, length, cross-sectional area, and the change in length. Now, for identical sample, this length and cross-sectional area are same. So, elastic modulus basically depend on the maximum force and the displacement. We can see that the maximum average force is increasing with the higher amount of carbon nanotube inside the PDMS. But if I notice in the column of maximum displacement, we can see that up to 1 weight percentage, the displacement is increasing. Now, if I go to 10 weight percentage, it started decreasing. Why it is happening? Because when during the test, the film was pulled vertically, since due to the higher amount of concentration inside the film, it was started becoming stiffer. That is why it was not getting able to pulled with the sufficient amount of force. And it was not possible to make a amount of displacement. So when I saw that the displacement is decreasing, that means my film is started becoming stiffer. So I stopped the test up to 15 weight percentage because I need a film with flexible or which has a very good elasticity, because I have to depend on the bending to check the change in resistance when I will flow the fluid through the channel. Then from the electromechanical characterization, where I check the change in resistance for different bending angle from 0 to 3 degree with 0.5 degree interval, it was found that the sensor was behaving quite linearly in terms of the resistance and bending angle. That means it was changing or increasing the bending angle, the change in resistance was also increasing. But in terms of the higher bending angle, a higher amount of standard deviation was observed. After that, I recorded the response and recovery time of my sensor, where I found that when I was increasing the bending angle from 0 to 3 degree, the sensor was responding quite immediately. For example, the response time was around 20 seconds. But when I left the sensor to go back to its 0 degree from the 3 degree, it was taking a large time, which is around 15 minutes. And this process was repeated for 10 cycles and to the similar value in terms of the response time and recovery time was observed. And another thing that was observed in case of the sensor, there is a hysteresis loop in terms of the response and the recovery time of the sensor. Now, after all this characterization, the flow type was observed. That means what type of flow will flow through the channel, whether it's laminar flow or turbulent flow or transient flow. Because in different type of flow, there are different methods which should I follow. Now, I tested 3 type of channel with 3 millimeter, 5 millimeter, and 7 millimeter diameter. And the velocity profile was like this for the flow rate from 0 to 250 microliter per second. And in every cases, it was found that the Reynolds number is less than 2300. Now, the Reynolds number is basically used in fluid mechanics to define the type of the flow. If the Reynolds number is less than or equal to 2300, we can say that the flow type is laminar flow. And here we can see that in every diameter of channel for these flow rates of the fluid, the Reynolds number that we have calculated are extremely less than 2300 value. That means we can say that the flow that was used in the channel of the sensor are laminar flow. After that, the position of the thin film or the sensor inside the flow channel was analyzed. For this purpose, the friction factor and the head loss inside the channel, also the pressure loss at different position of the channel for different diameter was calculated, and it was summarized that since the length of the channel is very small, for example, for about 5 centimeter, the head loss was very insignificant. It was not that much. So it was concluded that the sensor can be placed anywhere in between the channel except the opening of the channel. Because if I place my sensor at the opening of the channel, what will happen? When the fluid will flow through the channel, it will hit on the sensor directly, and it will give me some fluctuated value, even though it will give appropriate pressure. So to avoid the fluctuation, I avoided to keep my sensor of the channel. So I placed it in the middle of the channel to get appropriate pressure on the channel for the small flow rate of the fluid. So as I have shown this diagram earlier, this is the layout that was followed to check the sensor or test the sensor. From here, what was found? When the flow rate started, it was found that in case of 0 to 50 microliter per second flow rate, there was no that much change in the resistance of the testing sensor. But when I gradually increased the flow rate, for example, 100 or 150 microliter per second, it was found that there is a little change in the resistance of the testing sensor. And the significant change in the resistance was recorded when the flow rate was increased up to 200 microliter per second and 250 microliter per second. But another thing from this graph, we can observe that when we started the flow rate, the resistance was not changing immediately. It was taking a few time, for example, 15 to 20 seconds. to give a stable change in the resistance. So we can say the response time of the sensor was around 15 to 20 seconds. And that process was observed for 10 times for 5 millimeter channel, and it was observed that the change in resistance for different flow rate was different, gradually increasing when I was increasing the flow rate. But another problem arose here. Up to 150 microliter per second, the standard deviation of the system was not that much. But when I am increasing the flow rate, for example, 200 microliter per second and 250 microliter per second, it was showing a good amount of standard deviation, which is not good for my device. This was happening because when the flow rate was increasing, it was giving more pressure, and the film was bending in a fluctuated manner. That is why it was showing that much of a standard deviation. Now the same process was followed for different flow rates in another flow channel with the diameter of 7 millimeter. But for this increased diameter, it was observed that up to 200 microliter per second, there was not that much significant change in the resistance. But when the flow rate was increased up to 250 microliter per second, it was showing a good amount of change in the resistance. And finally, again, with 10 cycles, the response and recovery time of the sensor was observed, and it was found that the response time of the sensor is 20 seconds. That means when we start flowing the fluid through the channel, the resistance was not getting changed immediately. It was taking some time, and the average response time is 20 seconds. And when I stopped flow rate inside the channel, it was taking around 5 minutes to go back to its initial resistance. So this process was observed for 10 times, and it was found that the sensor was taking more or less quite similar time to response and get recovered. After that, the limit of detection of the sensor was observed, and it was found in case of 5 millimeter channel, the limit of detection is 35.64 ohm. And from these two columns, we can see that this 35.64 is matching with up to, it is not getting matched up to 100 microliter per second, because if you can see that in case of 0 to 100 microliter per second, the change in resistance is less than 35.64. But when I increased the flow rate from 150 to 250 microliter per second, it was showing a significantly high change in resistance than our limit of detection. Again, so from these values, we can say that the sensor with 5 millimeter flow channel has a limit of detection up to 150 microliter per second. That means this sensor cannot detect the flow rate of fluid less than 150 microliter per second. And same thing was performed for 7 millimeter diameter of the channel, and it was found the limit of detection is 38.55 ohm, and depending on the value, we can see that it is only applicable for microliter per second. So if I increase the diameter of the channel, the limit of detection is increasing. That means which is not good actually. The range of the flow rate is increasing, but our purpose is to try to measure as much as low flow rate. So if I want to conclude my research, I can say that the MWCNT PDMS film was fabricated with different concentration from 0 to 15 weight percentage. And in the fabricated film, there was no conductivity found less than 8 weight percentage. But if we increased the concentration, we could find a significant amount of conductivity in the film. And I used 12 weight percentage thin film where the resistance was 2.55 kilo ohm. And for higher concentration, the water contact angle was increased. That means the film was becoming hydrophobic, which is good for my sensor. And another thing I can say that from the elastic modulus that was observed for different concentration of MWCNT PDMS film was increasing for higher concentration of carbon nanotube into PDMS. And in terms of the electromechanical characterization, for different bending angle, there was change in resistance quite linearly. For the and for the system, the flow rate that was tested was within the range of 0 to 250 microliter per second. The response time of the system was 20 seconds, and the recovery time was 5 minutes, which is quite high. And the limit of detection of the sensor was 150 microliter per second. And this sensor can be useful in different biomedical devices, because we know that in biomedical devices, we normally control the flow rate of blood or any drug that we give, provide in the patient body in liquid form at a very small flow rate. But there are some limitations in my sensor. I have mentioned basic 3 limitations of my sensor. The first one, only 12 weight percentage film was tested for the final sensor. No other concentration of the film was tested in the final sensor, although they were fabricated and characterized. The second limitation of this device is only PDMS polymer was used to fabricate the film. No other good polymer can be tried to improve the performance of the film. And the liquid that was used is the water. I didn't got any time to test my sensor with other liquid. So against this limitation, I want to recommend something if anyone want to develop this sensor in future. The first one I would like to recommend is to increase the amount of carbon nanotube into PDMS. The second one I would like to recommend is to improve the flexibility of the film by using or by trying different or better polymer. And I think there is a scope to develop the sensor design. Since if you remember, I have shown you that the value that I have got from the performance of the sensor was quite fluctuating. So if the sensor design can be developed or improvised, maybe the sensor will provide stable value. And also, since the recovery time of the sensor is quite high, the mechanism can be find out the recovery time. So that's all from my side. If you have any question regarding my presentation, you can ask.